name is Callie Babbitt. I'm an assistant professor here in the Golisano Institute for Sustainability at RIT. And I'm really pleased to be able to join you all today, and I'm glad we were able to be more sustainable by connecting by video conference rather than by my flying or driving to Cleveland. So hopefully that's on a life cycle basis, that's a good alternative. I'm going to be picking up today, this afternoon, where Ewan left off earlier, going from some of the basics of energy to talking more directly about energy and sustainability, and hopefully bringing us to a point where we can begin to think about why we need to use life cycle assessment, why it's relevant for the development of sustainable energy technologies. First, I wanted to just briefly introduce the Golisano Institute here on the next slide. We are an academic program, one of the, I believe, the second in the country to offer a PhD in sustainability. We also have master's programs here in sustainable systems and in sustainable architecture. And our primary focus here is on sustainable industrial development and coming up with new technologies and new discoveries in energy, mobility, and production systems that we can take and transfer to industry. And so I think there's a lot of overlap between the research we're doing here and the research that many of you are participating on with this project. And so I look forward to hopefully collaborating with many of you all in the future. So I'll get started with a quick overview of what I hope to cover today. I first want to just sort of lay out a basis for why we're thinking about energy and sustainability and what I would call the conundrum that we see at the energy sustainability nexus. And a lot of that has to do with how we use energy, what the ultimate demands for it are, where we get our energy, and the trade-offs that are necessary, the trade-offs that we're going to have to deal with if we start to look at alternative energy solutions. So first we'll start with energy and sustainability, and I think that Ewan did a good job defining sustainability earlier, so I actually cut a few of my slides out talking about this, but we can go back one. I always like to, back to the first definition, I always like to talk to the students about how we define sustainability. And I am guilty myself of often using the term more or less sustainable, as if we're choosing between the lesser of two evils. If we want to be very fundamental about thinking about sustainability, we can look at the most basic definition of the word, which simply means something that can be continued on forever. Now, this is a challenging definition because obviously we live in a finite world and a seemingly infinite growth of our consumption and liberation of natural resources and emission of polluting chemicals. So perhaps when the more relevant way to think about sustainability is not necessarily the ability to continue on forever, but the ability to use our resources in a way, as the Brundtland definition that was mentioned earlier suggests, in a way that's both responsible to the citizens of the planet now and those in the future generation. And so on the next slide, I actually have one of my favorite definitions of sustainability, and this might be because I'm from the rural American South and like farming analogies, but this definition says sustainability means don't eat your seed corn. So a farmer at the end of a season will consume some of the resources, but also put aside some of the resources in the barn so that he's ready to plant, he or she is ready to plant in the next farming season. And this is very similarly to how we can begin to think about our resources. Building replenishing systems that can supply the future, but at the same time meet the needs of the present. And many modern definitions of sustainability, like this one, go on beyond this sort of past, present, future perspective and thinking about other dimensions of sustainability. It's about people, a robust workforce, strong communities, innovation, values, environmental capital, and all of these things I'm sure are particularly germane to the types of renewable energy technologies that you all are developing. Now, when we think about why sustainability is attractive, one of the reasons is because it's an idea that both industry and society can get behind. Because the appeal of sustainability is this idea of integrating environmental and economic considerations. And you can see this in this Venn diagram where we think about dimensions of social, environmental, and economic issues, and sustainability residing at the center of those dimensions, something being only truly sustainable if it does not compromise one of those dimensions. Another way of thinking about this, and a common representation, is the idea of sustainability as a three-legged stool. And if any one of these legs on the stool, whether they be economic, society, or environment, are shortened, the stool will topple over, and it's not a firm base on which to develop technologies. So the main points of when we think about sustainability, and I've asked you to remember these to carry forward into our future classes, are the idea that environmental issues cannot be isolated from social and economical issues. So the greenest of technology, as Ewan pointed out earlier, is not going to last if it is not cost effective and if it doesn't meet society's needs. Similarly, we also have to now begin thinking about equality not only within our current generation, all of the citizens of the planet currently, which we're pretty far way off from, but then also equality between our generation and then future generations to come. And so this is a pretty strong imperative. But when we hold both of those things in account, we can start thinking about energy and sustainability. So given that definition, we know that energy, availability of energy, of reliable energy, and what we can do with the energy is an essential factor in social and economic development. However, at the same time, our modern systems for acquiring energy resources and transforming those into these secondary forms that we use are responsible for some of the most serious environmental impacts on the planet. Now, in the next two slides, I have kind of a visual way of showing this. Now, I'll preface this by saying these slides are taken from data from gapminder.org. It's a wonderful data visualization site, and it's very powerful for looking at all kinds of different data in sync. And so what we have here, on the y-axis we have the Human Development Index, which takes into account a lot of different factors like literacy, equality, democracy, poverty or lack of poverty, environmental issues, things like that, and energy use per person. And we know that like gross domestic product or like other economic indicators, the more energy use that a society or a culture has at its disposal, the higher the level of development. What this graph also suggests is that this relationship is somewhat asymptotic, in that you get to a point in which you may continue to consume energy, but with no appreciable development of or enhancement of your country's societal well-being. So this says maybe there's a point at which we can develop and then we can curb our usage. But clearly, energy use is an important part of developing social well-being around the world. However, on the next slide, we can also see that there's a clear correlation between energy use per country on the x-axis and the yearly CO2 emissions per country on the y-axis. And this is on a log-log scale, but this is a clear linear relationship that holds true across different continents, which are shown in colors, which hold across different population sizes, which are shown by the area of the circles that you're looking at. And so even for countries that have relatively clean fuel mixes, this relationship is relatively constant. And so clearly, if we're going to do something about climate-altering gases like CO2 and to try to mitigate the environmental impact caused by climate change, the energy system is certainly one area in which we have to start. And just to look a little bit more in depth on the energy and climate nexus, what we have on this slide is what's called a Sankey diagram, S-A-N-K-E-Y, Sankey was an engineer pioneering the thermodynamic analysis of steam engines. And these diagrams are commonly used in sustainability to show the relationship between energy and material in different forms. And so on the left-hand side of this graph, what you see are sources, or primary sources of CO2 emissions. And on the right-hand side, you see the gases themselves. And so it's clear to see that energy in the orange, the dark and light orange, makes up most of the contribution globally to climate-altering gases. That's in the transportation sector, the electricity sector, and also the energy that's used in industry to make products. Most of those gases are carbon dioxide. So clearly, if we want to do something about climate change, energy is where we have to focus. And on the next slide, we can hone in a little bit further. Now this is another Sankey diagram. This is specific to the United States, and it's looking at just those carbon dioxide emissions from energy sources themselves. And again, on the left-hand side, we see the different primary energy sectors, natural gas, coal, and petroleum. And on the right-hand side, we can see the sectors in which those fuels are ultimately used. And so I've kind of circled on the left and right-hand side on the next slide to highlight the two sort of dimensions of this challenge. So if we want to do something about climate, therefore we want to do something about energy, we have to think both about how the energy is supplied, the fuels in which we are harvesting to get these energy sources, and then how it's used. It's very hard to see on this slide, but there's a tiny line up at the very top that says renewables. Right now, not in a significantly appreciable quantity in our total country's energy mix. So if we want to think about supply and demand in terms of energy and sustainability, let's start by talking about energy demand, because we want to, when we think about reducing our entire energy footprint, it doesn't make sense to create green energy for our current level of demand. First, we want to reduce that demand as far as we can, and then meet the reduced demand with a cleaner supply of energy. So where does our energy come from, and where is it going? There we go. Another Sankey diagram. I really love these, so you'll see them a lot. And in this one, this really hones in on the United States. It may be somewhat hard to read here, but certainly I would encourage you to study this after the fact. And this really focuses in further in energy use in the United States. The units are in quadrillion BTUs, and the thickness of the line indicate the relative quantity of the flow. And so what we can see is that most of the petroleum resources are indeed going to transportation. Most of our other fuel resources like coal, natural gas, and most of our renewable sources like hydropower are going into electricity production. But one thing I'll point out is the gray lines on the far right of the graph. Over 60%, or close to 60% of the entire energy inputs in the United States are lost, are rejected energy. And so this really ties into the thermodynamic lecture that you all heard earlier today, in the fact that when we think about the conversion from primary into secondary, or primary into direct sources, we're losing most of the usable energy. And so the ultimate energy that's used is only about 40 to 45% of the inputs. So clearly there's an opportunity here for reducing that wasted fraction by making our technologies more efficient, at least to their thermodynamic limits. But we also want to demand less energy. So on the next slide, we can look just at our end-use sectors. And again, this is specific to the United States. Most of our energy is going into residential and residential and commercial buildings. So it's both electricity and also direct use of natural gas. Industrial sector consumes a significant fraction, and then transportation on a net basis of the entire portion of energy consumed uses the most. And again, this is total primary energy consumed by each of these. See how this has changed over time, and the troubling conclusion from this graph which shows the net use by each of these sectors over time, is that there's a clear upward trajectory. Now, we see there's been some downward swing in the industrial sector. Unfortunately, that has not meant that we've totally reduced our industrial footprint, but rather we've moved a lot of our industrial operations offshore. We've begun exporting our pollution, so to speak. So when we start thinking this life cycle systematic view, we can't necessarily just look at the United States. We also have to look at where our products come from and where things are being manufactured and disposed at the end of life. But on an overall basis, consumption is going up over time. Now I see on the next slide, I've honed in specifically looking at electricity, because I know many of you are doing research on novel materials for energy production, and most of that will probably be in the electric generation sector. So if we look only at electricity, we see that most of that is used in residential and commercial sector, and that a lot of that is attributed to energy use in buildings. There are #1 electricity consumption in the United States, and that trend is fairly consistent around the world. Buildings and the heating, the cooling, the appliances, etc., consume most of the energy, electric energy that we produce. So it stands to reason that if we want to think about reducing demand, buildings are a great place to start. And so I want to give a small example here of what happens with efficiency. So on this slide, what you see is just an example of an energy efficient technology. The use of double or triple pane glass for construction of homes. So in the last 40 years, the use of the energy efficient technology, like double, triple pane glass, has increased very rapidly. A lot of this has to do with the cost going down, as well as the direct benefit that a homeowner might get because of energy savings. So we can see this across the board in terms of homes. Homes and of course other buildings are getting more sustainable, but we're also building more homes, and the homes are getting larger. So in this graph, what we see is million BTU per housing unit in the blue, which is a clear downward trend up until about 2010 when this graph ends. But the total number of housing unit is going up every year. And so even if we're making small incremental gains in the efficiency, not only of our homes, but of things like automobiles or industrial processes, we're also consuming more. And this leads to what we call the rebound effect. This is the idea that improving our technology to make efficient use of energy can sometimes be offset when users change their behaviors or when other factors lead to increased consumption of electricity. So I'll give a personal example that I'm guilty of. When we bought our new home, we replaced the lighting in the basement from incandescent to compact fluorescent bulbs. But because of this, I've now rationalized that it's probably okay for me to leave the bulbs on all the time. And this is consistent with what we know about how people behave with green technology. Typically, if you get an energy savings, like you have a vehicle that has a lower gasoline consumption, like a hybrid vehicle, people tend to drive more or to use the product more, like the compact fluorescent bulbs. So the bottom line to this is it's good to be aware of this and design products that maybe try to get people around this rebound effect. But it also says that reducing demand alone will not solve the global energy challenge. And if we want to think about sustainability in energy, we also have to think about energy supply. So the third part, what I want to talk about now is energy supply. And I'll start just by simply reviewing what we know about energy consumption in the United States currently. So on the next slide, I have a pie chart, again looking at the United States, and again this varies somewhat by country, but it is relatively consistent in most developing countries. And in our total end-use consumption of energy, where we get it is almost primarily from fossil fuels. Coal, 20%, petroleum close to 40%, natural gas. Nuclear power accounts for about 8%, and then renewable energy only about 9%. Now, I want to make some comments about what we can currently consider to be renewable energy. A big portion of this is hydropower, and so we know that of the renewable energy, most of that is made up by hydropower, which is relatively geographically constrained. There's only a few places, New York State being one of those, that is significantly reliant on a large fraction of hydropower. What's interesting, though, is in this renewable energy category, we're also getting credit, so to speak, for, say, burning municipal solid waste. That, in the accounting that the U.S. does, contributes to that biofuel category. We're also counting things like burning wood, which is a common practice in, say, the pulp and paper industry. So, while these are technically considered or labeled under the category of renewables, they're not necessarily what we typically think of as renewable forms of energy. And so it's kind of important as we go through this is that I'm going to primarily be talking in terms of renewable energy about things like solar and wind, but there are other categories that fit under that as well. Now, before I go on, I just wanted to check really quick and see if there was any questions so far. We good? All right, well, I'll continue. So, I want to talk really briefly, instead of getting into the mechanisms of how the different energy sources are produced. I think that's important, but I think it's more important to be able to think about what the future holds for our energy supply. And despite the naysayers about fossil fuel availability, it's an unfortunate reality that we will have a low-cost stock of fossil fuels domestically and globally for quite some time into the future. Now, it's debatable about what that cost might be, and that will certainly change with prices or discovery of new resources. But one of the major limiters of renewable energy are low-cost alternatives. So, on this graph, for example, it shows some scenarios of future oil prices, which will have a major role in that petroleum sector of our energy supply. And so we can see anywhere from $50 to $200 per barrel in 2010 dollars. And this makes an enormous difference when you take these numbers and put them into scenarios of, say, electric vehicle adoption. It significantly changes the readiness with which alternative energy technologies will likely be adopted. And it's very difficult to know and to forecast how this may change in the future. So this will be one of the factors that will really determine whether or not there are significant incentives or barriers to renewable adoption. We also see emerging challenges and future in the natural gas sector. So one of the things that I'm sure that many of you all are aware of, and is certainly a major issue here in the United States, is the availability of shale gas and the hydrofracking debate that is certainly gripping our area of the country, if not others. But one of the challenges here is that natural gas, which is traditionally mined very similarly to crude oil, is now being identified in shale gas form in many places in the United States. And it's anticipated that this extracting gas using this technology by drilling deep below the aquifers into these shale formations, pumping in a hydraulic fluid, fracturing that, and then extracting the fluid and the natural gas for refining, could provide a low-cost alternative for instead of renewable technology. So this could be a substitute. So there's a lot of sustainability questions about this. Maybe it's better than coal. Maybe it's not. Maybe the unanticipated environmental consequences of this technology will be catastrophic in the area. So there's a lot of emerging risks around some of our traditional fossil fuel sources that we have to kind of take into account. But coal is certainly the one that looks to be the most problematic in the United States, especially for our electricity fuel mix. Now, this graph is very frightening to me. If you look at the very top of this graph, in the very top triangle, is the current amount of coal that we know of that is currently being mined in active mines. However, when you start extending the analysis to mines that we have fairly high confidence that we'll be able to recover coal from, as well as a demonstrated reserve base, whether it is or is not economically viable, and then additionally going down into that identified resources category, those are mines that we may not know of currently, but we can extrapolate our current knowledge to infer that they must be present. If we continue, but all of this, suffice it to say, is that if we continue extracting and using coal at the rate we are currently seeing, about a 0.4% growth per year, we have 170 years of fairly well-assured supply. In 170 years, if we keep extracting coal at this much, we're going to run out of the sustainable atmosphere before we run out of coal. And so this is a particular challenge for transitioning our electricity supply, where in the United States, 40% of our electricity, close to 50% of our electricity comes from coal, transitioning our electricity supply to a greener mix. Coal is also, unfortunately, the most polluting. It attributes most of the CO2 emissions in energy sources, and wherever you have coal, you have almost every other element known to man: arsenic, lead, mercury, selenium, etc. So when this coal is combusted, you're liberating an enormous spectrum of potentially toxic metals. So it's a harbinger, an indicator of the environmental footprint of our energy supply sources. And because of this availability, the costs are continually low. So on the next slide, we see a comparison of costs, and these are at an electricity power plant, the amount of the fuel costs, basically, that they have to pay in order to generate our electricity. Natural gas is pretty variable. Residual fuel oil, which for a long time was used as a backstop energy supply, has gotten very expensive. But coal has maintained a relatively low cost. And so when we see peak electricity demand, like when everyone wakes up in the morning and takes a shower and then comes home at night and turns on the air conditioner and start cooking, those are the times in which the Electric Regulating Commission begins to think about turning on power plants that are less efficient but are very cheap to operate, and those would happen to be the coal plants. And so if the cost of this traditional technology is continually low, there will be an additional barrier for renewable energy technologies to penetrate the market. Now, the caveat to all of this is that this does not account for policy mechanisms or for incentives that different states may adopt in order to meet, say, renewable energy targets, which specify that a state has to have a certain percentage of their energy mix come from renewable sources. So what are these renewable sources, and what are some things that we have to think about? I've sort of skipped over nuclear altogether because that's another issue to deal with. But we would include biomass, and which we talked about earlier includes things like burning landfill or burning solid waste, biogas that's recovered from a landfill, wood waste, etc. Hydropower, geothermal, and then wind and solar. And so if we want to think about increasing the prevalence of these in our fuel mix, then we have to start thinking about what some of those challenges are. And so what we see is, as I've kind of been discussing already, that because we have very low cost alternatives, the relative cost of producing energy via renewable fuel mixes is still very high. The other challenge is that many of these energy supply, particularly wind and solar, but also some of the others, have very strong, are very intermittent. So obviously we're only generating solar power during the day. which necessitates additional technology to store that energy, which some of you all may be working on as well. What's also very challenging is that these fuel mixes, or that these sources are also variable and vary significantly across the United States. So the ability for us to generate solar power here in Rochester is a little bit different from the ability that we had when I lived in Phoenix, Arizona. So depending on where you live, you're able to capture energy with relative comparative ease, but then that energy has to be over the grid and disseminated to the ultimate customer. We typically see about a 9% loss in distribution and transmission of electricity on the grid. So to minimize that, you want to be able to use energy where it's produced. And really, to the point of this whole class is the idea of the unanticipated consequences that come up due to some of these new technologies. And so I'm going to go through a couple examples now about what some of the regional challenges are, what some of the trade-offs are. So this first example is biomass resources, and it's not surprising that we see very high concentrations. These are the maps that I'll be showing are all from NREL, which does a lot of assessment of energy across the United States. And you can see a color scale over on the right-hand side that indicates what the color corresponds to in terms of, in this case, tons of biomass, 1,000 tons of biomass per year. So it's not a surprise that you see a lot of this in the heartland, and we certainly think about crop-based biofuels, corn, switchgrass, etc. But there's a lot of this also in very densely populated areas. And again, this has to do with the use of waste products or landfills. One of my students is from Alaska, and so when he saw the little yellow dot on there, he was kind of surprised about biofuels in Alaska. But it turns out that that's the spot in Alaska where all the waste is sent and it's burned to make electricity. So like I said, that counts in the biofuel mix. But certainly for a sustainability perspective, we're very concerned about sort of these life cycle impacts, and that's gotten a lot of attention from biofuels, especially corn-based ethanol. Next slide, you'll see a very simplified example of a biofuel life cycle in which you're getting solar energy. It's converted to sugars by the process of photosynthesis. The crops are refined, maybe used for food products, but also used for say in this case, biodiesel or other products, used as a renewable fuel. And of course, there's CO2 that's taken up when the fuel is eventually burned. But that CO2 is produced in the same amount that the plant took up during its growth phase. So the idea is that it's a net CO2 neutral process. But recently we've had a lot of concerns about whether this really is a net CO2 neutral process or not. So there's obviously impacts and inputs along the way. We're not, as you all learned earlier today, thermodynamically, you're not going to have a perfect conversion, and it's going to take a lot of energy inputs to get the energy out in the biofuels. A lot of those take the form of agricultural inputs, fertilizers, agricultural equipment. But one of the most surprising things about biofuels is land use. It takes a lot more land to obtain these materials than our traditional fuels. And because of this, because of the transformation of, say, farmland into cropland, we see what's called both direct and indirect land use change. Direct land use change is when it's directly converted from one application to another. And a lot of times this carries with it the carbon that's stored in the soil is released into the atmosphere, causing a net CO2 increase. What's more concerning is this idea of indirect land use change. For example, if we use land in the United States to produce crop-based biofuels, does that mean that it might induce another country to do the same thing? So for example, if Brazil decides to translate rainforests into crop-based systems, that will cause a net depletion of the CO2 or the carbon stored in, say, a rainforest and a release to the environment. So because of all these questions and uncertainties, when you take this very broad life cycle view, there's been huge uncertainty in the estimates of, say, the carbon footprint of corn-based ethanol. So on the next slide, there's a couple estimates from different sources. So on the left, we have a graph produced by Argonne National Lab, which looks at the net life cycle emissions of transportation using either traditional gasoline or corn-based ethanol. And they find that on average, corn-based ethanol has about a 20% reduction over the traditional supply. But on the right, we see an estimate by the EPA, which says that the life cycle CO2 emissions from corn-based ethanol could be as much as 50% below gasoline or 50% higher than traditional gasoline. So there's a lot of uncertainty around biofuels right now. And a lot of this is due to the fact that as we're developing this technology, we're also becoming more astute about thinking about life cycle trade-offs. It turns out that when we do a retrospective assessment of other technologies like coal, nuclear, natural gas, etc., you also see a lot of variability in those assessments as well about what the net environmental impact was. It's simply that at the time they were in development, we didn't have the tools at our disposal or the knowledge that we needed to take a life cycle perspective into account. So on the one hand, results like this are sort of confusing, and they end up leading to a lot of concern about what types of biofuels we should choose, but it's also a good sign that we're beginning to think about things on a life cycle basis, which is hopefully a good indicator for our moving forward. On the next slide, we see a map also provided by NREL with the average wind speed at 80 meters, which is one of the heights they assess for wind turbines across the United States. And even more so than biofuel, we see a really significant variability in which right along the central corridor of the United States and then mostly along coastlines, we have significant availability of wind. But to take that wind resource and to take the electricity that's produced from that and transmit it to the rest of the country would require significant infrastructure that we don't yet have. And so this is a resource we're not able to yet capture, but it's probably one of the fastest growing renewable energy supplies. One of the major considerations, though, are some of the trade-offs associated with the production. So on the next slide, it's just shows sort of this idea of NIMBY, or not in my backyard, that we currently have with respect to siting of wind turbines. The interesting thing about wind power is that it is the power that a turbine can generate, it increases non-linearly or with a power law with respect to how high you can place these turbines and how big the turbines are. So we get more power, very large, very big turbines. No one wants very large, very big turbines in their area. And even here in New York, where we have a lot of wind generation capacity, there's a lot of backlash against this technology. And so one of the trade-offs here will be getting this idea of social acceptance for a technology like this, as opposed to something like coal combustion, in which you're relegating the power generation to one facility that might be put in one part of town, and if I don't live near that part of town, I'm not worried about it. So there's a little bit of social acceptance for wind that we have to deal with. Now, solar is probably the area that many of you are most interested in, and when we think about solar, there's a lot of materials research being done, both in concentrating solar power, in which we're using a mirror or something, a parabolic trough, to concentrate the power or the incoming radiation for very high efficiency recovery. In the built environment, we think a lot about solar thermal, or the direct heating of water from solar radiation. And what I would imagine many of you all are doing research on are new photovoltaics for converting solar power or solar radiation into electricity. A couple maps, again from NREL. The prospect for concentrating solar power is relatively limited to the southwest. And when I lived in Arizona, I was always shocked that you didn't see solar panels or large installations of concentrating solar power everywhere. Now, concentrating solar power is particularly difficult because it is a very expensive technology with significantly high upfront capital cost to producing it. It also requires a very large land footprint. And what's interesting is when you begin again to think about the social ramifications of this technology, you begin to get in dialogue with people who live in the American Southwest, who really treasure the landscape and the appearance of the area as a natural resource in the same way that we would energy. So there's a lot of social resistance to putting up large installation of solar technology there, because it changes the views and the vistas of that grand American Southwest that we typically like to see. So it's kind of an interesting trade-off, but one we really have to take into account. On the next slide, a similar map for photovoltaic. The prospect is a little bit better. We have photovoltaics here on the roof of our new Sustainability Institute in Rochester, and with a generating capacity, I believe, of about 3.5 solar hours per day. So enough to where it makes a sizable contribution to our net energy demand. And so photovoltaics is where we see a lot of growth in our energy supply, particularly due to rapid advancement in new technologies, third generation solar cells, rapid improvement of efficiencies, which you can see at a research level on the next slide. So again, from NREL, we're looking at research cells, at least best reported averages, and this slide is probably a year old, so certainly some of these have been surpassed by now. But the challenge is that a lot of the technologies that many of you might be working on in terms of emerging technologies like organic photovoltaic, dye-sensitized cells, quantum dots, yes, those, I'm guessing those are ones that many of you all have particular interest in, still at very early stages of development, but a lot of promise in terms of technology. But still many of these, because of the relatively low efficiency, are not yet competitive with traditional power plants. So this, even though we know that our power plants are very inefficient because of the thermodynamic relationships mentioned earlier today, they're still getting an average efficiency of, say, 30 to 40% of the amount of electricity that's produced compared to the amount of primary energy that's input. And a lot of our solar technology is still well below that. So when you think about this in terms of costs, on the next slide, we often use the idea of levelized cost to compare between technologies, because the technologies are very different, especially in the idea that there's only some of these that you can run overnight, the rest are relatively intermittent. So what levelized cost is the cost in real dollars per kilowatt hour that takes into account all of the construction, the operation of the electric power plant over its assumed financial life, and taking into account its capacity, or the amount of power that it can generate over that lifetime. So obviously for some of these, that capacity is comparatively low. And so this takes into account a number of factors. In the orange, the investment to the transmission of the energy, and a lot of that may have to do with conversion and DC AC inverters, etc. The variable cost, or variable operations and maintenance cost, is significantly attributable to fuel supply. So for any of these that require fuel, like coal or nuclear, etc., you see a lot of costs associated with the fuel. But for many of these, the fixed costs, especially for renewable energy, are pretty high. And again, this just has to do with the fact that you're not generating electricity all the time. And so when you normalize those fixed costs over the total life cycle and the amount of the power that can be produced, it's relatively high. But on a positive note, we begin to see some technologies like wind, etc., beginning to be fairly comparable or even lower in some cases with our business as usual case or our typical coal combustion. The challenge then will be to improve the cost of the rest of the electricity, of the rest of the renewable portfolio. And so in terms of this, just using this levelized cost as a starting point, what would it mean to actually reduce these costs, and how could we then advance renewable energy? So first off is simply deploying more capacity. So if we look on the next slide, more capacity means that there's more availability and the transmission costs are normalized over more generation. Certainly the efficiency of the conversion of energy is an important parameter, and I would suspect that many of you are working on that very problem using novel materials and new device conversion or device level efficiency improvements. Certainly though, we have to be also thinking about energy storage technologies at the same time, especially for these intermittent supplies. Whether or not that's storing the energy and being able to use it to offset, say, peak electricity demand, or whether it's to complement some other type of technology. And then, of course, as we go along this technological progress curve, we can also look at opportunities for reducing production costs and the upfront costs, which there will be some natural reduction of as we begin to scale up research level technologies and as these newer renewable energy technologies become more widespread. So these are sort of some of the challenges that we have to overcome to improve the adoption of renewable energy and also improve the costs. So before I move on to the last part, I just wanted to check again to see if there was additional questions or that have come up along the way, or if anyone watching the webcast has sent in questions.
The levelized costs take into account the subsidies provided by the government as well as increased regulatory prices on different materials?
Okay, that's a great question. This assessment, which is done by the EIA, which basically every year comes out with assessments of renewable energy, does not take into account subsidies or any sort of policy. It takes into account some of those policy related things are folded into the variable costs in terms of the fuel costs, but it does not take into account any subsidies. And that actually turns out to be one of the ways in which a lot of these technologies are being brought into the mainstream. I'll give a quick example. Here in New York State, there's a number of incentive and subsidy programs for businesses to adopt renewable energy, solar or wind technology. What's also interesting is that businesses are also very concerned about their basic operating costs, which in New York State, their cost of electricity is not determined by the total amount of electricity they consume, but often by the amount of time they spend consuming energy at peak times. So the size of the peak of the electricity they consume in those times. So a lot of the industrial businesses here in New York State are very interested in shaving that peak or leveling off their electricity consumption so that it's flat over time. So there's a number of businesses that have been put in place to go to companies and to look at ways of using battery supply or battery banks to store or to buy extra electricity or to store renewable energy when it's very cheap, and then to use that energy to lower that peak cost. So it's an interesting concept because for businesses, they're actually reducing their costs not because of avoiding electricity consumption in total, but rather reducing that peak, but they're paying for it by tacking on a solar or wind system and then using subsidies or state level incentives to pay for that. So this does not take into account any of those subsidies. This is just the basic costs, but there are those are becoming more and more effective at getting some of these technologies into the marketplace. And we'll talk about this point here, this idea of advancing renewable energy, and we'll go into the fourth part of the talk, which I think is probably the most germane to the issue of life cycle assessment. So on the next slide, I've tried to raise the issue of trade-offs. And this is where I hope that a lot of you all will begin to consider how advanced energy technologies may lead to unintended consequences, and the need for what we call a systems level perspective. So if by advancing new renewable energy technologies, we're able to reduce fossil fuel usage, then certainly we've made a huge environmental gain by reducing fossil fuels consumption and reducing the amount of emissions that go along with that. However, the question of what is happening in its place. So many energy technologies require the extraction and consumption of scarce materials. So cadmium telluride solar panels, for example, require the mining of tellurium. And so a question that as sustainability practitioners we have to begin to ask is, which is worse, consumption of fossil fuels or consumption of tellurium? And that's not a question, it may seem very obvious to us as in being concerned about energy and the environment that getting rid of fossil fuel consumption is our #1 priority, but it's a valid question to begin to think about, are we trading one scarce resource, petroleum, for another or other types of fossil fuels? So as we move towards renewable energy solutions, we may need to extract and consume or dissipate scarce materials. These are materials we may not have the ability yet to recycle back into productive use. Maybe we're going to be developing technologies that are very energy intensive themselves, and they may not have a very favorable energy payback time. In other words, it may take a very long time before the amount of energy saved by their use can offset the amount of energy put into their manufacturing. Similarly, we may also be introducing new toxic emissions. So instead of the heavy metals that we were generating during coal combustion, we may instead be using nanomaterial or new types of metals that we don't really have a toxicity assessment for yet. And ultimately, taking into account a life cycle view, we know that we're also likely to generate new waste streams. And so I kind of just want to go through a couple examples to get you all thinking about this idea. So I like to use electric vehicles as an example. I do a lot of research on lithium-ion batteries and what may happen when we begin to adopt electric vehicle technologies prevalently. And so on the surface, we can think that, by adopting electric vehicles, we're reducing our demand for petroleum, which we saw in the U.S. was our #1 of primary energy supply that we consume. And this may have a net sustainability benefit. But as sustainability practitioners, we also have to take this systems level perspective. And so we have to not only consider the electric vehicle system itself, but all the ancillary systems that it touches. So the electricity to power this vehicle has to come from somewhere. If it comes from the electricity on our current grid, then that means we're going to be consuming an awful lot of coal and natural gas and producing CO2 emissions to produce it. Now, maybe, as you see on the bottom left-hand side, we're getting the electricity from a solar power station, and I think this example is in Florida. Well, then that certainly is not causing net electricity emissions, but we have to build infrastructure for this. We have to generate and mine and extract and process those materials to make the solar panels. We obviously have to store the energy somewhere, and although I've got a couple examples of lithium-ion batteries in the top right-hand corner, very few of those are the very large ones that will end up in the vehicle, but they're representative of the challenge that now we have to concurrently develop this other energy storage technology. And then the small graph that you see there is lithium extraction over about an 80-year period. And so we see a significant amount of lithium, a significant rise in the extraction of this mineral over time due to demand in applications like batteries, mostly to date in consumer electronics, but increasingly so in electric vehicles. And then at the bottom, the reality that when we're done with the vehicles themselves or the batteries that are in them, we have to think about recycling them. And often that involves a pyrometallurgical technique, or like this one that's shown here, where they smelt these batteries down to get the precious metals, or even a hydrometallurgical route in which we're using acid leaching to extract the valuable materials. Neither of those technologies is emissions-free, and both have serious environmental and health risks. So by adopting electric vehicle, or fill in the blank, adopting any type of renewable energy technology, we have to begin to think about all these systems level effects. So just to kind of dive into a few of these, on the next slide, this is a report, this graph is from a report on critical materials that was put forth a couple years ago by the Department of Energy. And it really sparks this, and in the academic community, there's a lot of interest right now in what is the material impact of deploying renewable energy systems. And so this graph also includes lighting, LEDs, and phosphorus used in lighting, which I've cut off here to focus, but if some of you all may be interested in that as well. So photovoltaics, magnets used in wind turbines, magnets and batteries used in motors and batteries for electric vehicles. And we begin to look down the left-hand column at the minerals, the metals that will be required to produce and use each of these renewable energy technologies. Many of these are scarce. Almost very, very few of these have any recycling infrastructure at all, very low recycling rates, if that infrastructure does exist. Many of these have not been assessed in terms of their toxicity. And the question about their long-term supply is still very much in debate. There's also this issue of mineral security. The United States, just focusing here on the United States, I know there's a lot of international participants as well, but the United States imports most of these materials. And so there is a risk of supply chain disruption due to different material origin. So if we then take this material and think about it in terms of criticality, on the next slide, we can see that there are some materials that are more concerned than the other. So the way that we typically think about criticality is in two dimensions. On the y-axis is its relative importance to clean energy. So in other words, if this mineral was no longer available, could the technology in which it is used still be made and used? And on the left-hand axis, from low to high, we look at supply risk. And this takes into account two factors, well, many factors, but two general categories. First, simply how much of the mineral we know exists and how easily we can mine it. And secondly, what is the chance of a supply chain disruption due to political or supply or other constraints along the way? And so we begin to see that there are some materials that are in that top right-hand corner that are particularly concerning, be considered to be critical. Neodymium, for example, many of these are used in magnets and other technologies. And then in the yellow quadrants on the X and Y, we see materials that we would think of as being near critical. So I like to use indium as an example. We use indium in every flat panel display. All of your smartphones that I'm sure you're not looking at right now in lieu of the listening. I'm sure you all are better than my students. All of your smartphone flat screens, all of our photovoltaic, the transparent electrodes, almost every usage like that requires indium. And this is quickly becoming a material that there's significant concern about, and there's a lot of work being done right now on manufacturing indium tin oxide ITO-free electrodes for different applications. I mentioned tellurium earlier, also a mineral that's very essential for certain types of our photovoltaic applications. And then in the bottom left-hand corner, materials that as of yet are not thought to have particular criticality issues, but there may be other issues as well. And so cobalt, for example, is one that we talk about a lot in the battery market. Cobalt is used in a lot of lithium-ion batteries currently, but as we are looking to produce cheaper and more easily produced lithium-ion batteries for electric vehicles, we actually are seeing shifts away from cobalt, not because of criticality, but due to performance as well as cost. And this is a relatively short-term matrix. This only projects to 2015. There's a second matrix that I haven't included here. It's very, very similar for the medium term beyond this. Some of the minerals move around a little bit, but the bigger challenge is that we have a lot of uncertainty beyond 2015 about what the issues are. So certainly if any of these materials is on your list of ingredients, so to speak, for your renewable energy technology, you have to start to think about the scarcity, the criticality, the cost, and the potential environmental impacts, all of which are currently unknown. On the next slide, I wanted to bring up another point that I think will be very many of your research projects is the use of nanomaterials for improved efficiency or for material modulation for improved absorption of solar energy. And we see huge increase in the use and the type of nanomaterials used in renewable energy technologies, whether it's a carbon nanotube in H there that's used in the anode of a lithium-ion battery, or perhaps a fullerene, like a buckyball type structure like D and F that might be used in an organic photovoltaic. There's enormous increases in nanomaterials for renewable energy, and I suspect many of you are working on this topic. One of the challenges, though, is that nanomaterials are, in the sustainability field at least, a big unknown. They're a big question mark. One of the things that we do know, though, is that currently, because production is relatively small, we're not often a very scaled up process, the energy that it takes to make these materials is enormous. So on the next slide, I have a couple examples of the total primary energy required to produce either a fullerene or single wall carbon nanotube. I won't spend a lot of time talking about the fullerenes because that's the case study that you'll be hearing about next Monday. But I just would like to kind of show a range of estimates for some of these materials. Fullerenes, 13 to 100 gigajoules per kilogram. Carbon nanotubes, 100, 600 gigajoules per kilogram. Now, it's probably difficult to kind of think about what that means in an absolute sense, but you can easily compare that to other materials that are commonly used in renewable energy systems. And it's clear that nanomaterial production is on an order of magnitude higher than most materials that we're used to using. And one of the common arguments is, oh, well, you're not using very much of it. It makes up a really small fraction of your final device mass. But it actually turns out that even less than 1% of the mass being made up of nanomaterials can cause a significant increase in the total energy payback time for a device. And Anik Antil from Clemson will be talking about that next week. She is one of the graduates from our program and did her dissertation on this topic. So I think it's important to always keep in mind that the idea of the energy that it takes to produce a renewable energy technology as well as the energy that it can produce. And then nanomaterials as a whole are a very hot topic when it comes to environmental health and safety. So on the next slide, this is just a very rough schematic of the challenges that we face with respect to nanomaterial release to the environment. When nanomaterials are being synthesized, there's obviously inhalation risks that we don't really understand yet. When they're contained in products, they're considered to be relatively safe, but if a product is weathered in the environment or goes into a landfill and breaks down, right now it's a big mystery as to whether or not it's going to cause some sort of health or carcinogenic effect, or whether inhalation might cause lung damage or something like that. And part of the challenge is that because of their size characteristics and because of their chemical and physical properties, nanomaterials don't always behave as we would expect in the environment. And so a lot of the methods and findings that we've developed for other new materials can't be directly applied. For example, if you have nanomaterials that are released and then agglomerate or absorb to soil particles, they're going to behave in an entirely different way than if they were going to be released in a pure form. And so this is a real challenge right now in the environmental health and safety community, as well as in regulatory efforts. And so people have a lot of concern about nanomaterials in the same way that we've heard people have concern about genetically modified organisms or other sort of hot issues. And there's not a lot of information out there to tell the public or to tell researchers. But it'll be very important is to think about these potential issues as you're working in the lab even, and taking environmental health and safety precautions there. But it clearly will be a question we have to answer as to what the potential unintended consequences of these new materials might be in our energy devices. And then finally, I want to kind of touch on this idea of new waste streams that might be created. Now, on the left-hand side of this graph are some rather disturbing, in my opinion, photos that are some of the worst-case scenarios that we see in terms of our current mismanagement of electronic waste. The reason I like to talk about electronic waste, sort of like why is this relevant to renewable energy, is that we can learn a lot about what not to do in this case. So when consumer electronics are being rapidly proliferated and adopted in society, no one was thinking about how to manage them in the waste stream. And so as a result, we ended up with, currently there's no federal policy about how this material has to be managed. There's not enough recycling infrastructure here in the United States, and there's not a lot of profit to be had from some of this recycling. So as a result, much of this material is exported to developing countries where it's often managed in a very informal fashion, resulting in severe environmental and health impacts. So all of those cables that all of your electronic devices have, power cords, etc., they all contain copper, which we see in the first graph, or the first picture, being burned. The plastics being burned off of the wires to get the copper inside. And in the second graph on the left, we see the water bodies near some of these informal recycling facilities that are being polluted by the acids used to leach gold out of circuit boards and then dumping the materials there. But the point is that we can learn the lesson that if you introduce new materials and new products into use and do not simultaneously think about how they have to be managed at the end of their life, then you're going to, by default, create a waste management nightmare. So then the question becomes, what will happen as renewable energy technologies and devices enter our waste stream? So obviously the shattered PV system and the burning wind turbine here are sort of worst case scenarios, but the question is, what do you do with a wind turbine when it is decommissioned? Well, most people think we don't have to ask that question yet because we've got 20, 30, 50 years before this material will really begin to enter the waste stream. But if we wait that long, we won't be able to respond. The other point is that earlier when we were talking about advances in efficiency and reductions in costs and incentives, the question is this: there may come a time in the future in which it's cheaper to replace, say, a photovoltaic that is not yet at the end of its life with a newer version because the efficiency gains have accrued so quickly. If this is the case, we could actually be seeing some of these materials enter the waste stream well before we anticipate. And so we have to be very proactive about designing devices and materials, etc., so that we can recover some of those critical materials, so that we can recycle them safely, and so that ideally we can keep these minerals in a domestic supply chain, which reduces some of that supply risk that factors into the criticality. So all of these point to these systems level considerations that have to be taken into account for the new renewable energy technologies. And so just to very briefly recap some of the main points that I hope you have gotten from today is that certainly as we think about global sustainability, there is no question that energy has to be at the central part of that dialogue. We have to be thinking about how to supply energy to people who do not have it, and then how to make that energy cleaner and more safe for everyone. Energy efficiency, though, and making our devices and systems and buildings more efficient will only get us so far. Number one, we're constrained by thermodynamic limits, of course, and number two, people will always consume more. So efficiency is somewhat subjective to the rebound effect. So we have to then say, if we know that we have some baseline level of consumption that will always be there, we have to transition to a renewable low carbon energy supply. And because we can accept as sustainability practitioners that the supply will have trade-offs, we have to have the ability to assess those trade-offs over the entire life cycle, all the way from the extraction of minerals and other materials, processing, the use, and then the ultimate disposal or management at the end of life of these products. And so that's exactly what we're doing when we use the methodology of life cycle assessment, is looking at quantitative methods and metrics for actually conducting that type of trade-off analysis. And unfortunately, what you'll probably begin to realize by the end of Wednesday's class is that there are never any easy answers. And so there's always going to be room for some value judgments, policy, and other considerations to factor in. For example, renewable energy may have less carbon footprint, but it may have higher mineral scarcity. It may have less acidification potential and higher ozone depletion potential. So depending on what environmental impact you're looking at, and depending on what the system you're describing, there's never an easy, it's a perfect, ideal solution. And so you have to have the methodology in hand in order to quantify those trade-offs. And so that's what I really hope to get across on Wednesday, in which we'll begin to start talking about life cycle assessment. Now, if anyone is interested in sort of reading up on the topic in advance, I certainly can recommend some resources. The EPA, the United States Environmental Protection Agency, has a good resource that's called LCA 101. I'm happy to send that out if anyone's interested, and it really describes the methodology in full. But I'll just kind of summarize by saying that I teach an entire course just on LCA. So the challenge of condensing it into 2 hours is very daunting, and we'll only begin to touch on the methodology, but we'll keep coming back around to it throughout the rest of the class sessions. But I hope that it's something that some of this has sparked your interest and desire to learn about LCA, and I really do hope some of you all will think about using it in your research, and I'm always happy to collaborate. So I think we have some time for additional questions, comments, concerns, or anyone on the webcast that sent in questions.
Callie, I'd like to bring up something. When you talked about the potential access to coal reserves for, say, the next 170 years, and the question regarding, the sort of CO2 emissions aside, we had a talk here last fall from, I can't remember her name, from the University of Oklahoma, or Oklahoma State, and one of her arguments was how long it would take to get a electrical system that was powered, let's say, largely by renewables, or certainly non-traditional forms, so not coal, not gas. And that might, she said, that might take 100 years to put into effect. And I raised the point that that's exactly why, in contrast to what she was suggesting, we should be thinking now about potential alternatives, because even though there may be 100 years, 170 years, there's not much difference between that of coal, the amount of time it takes to replace the electrical generation, we do not just do it tomorrow, right? Because there's considerable changes that need to be done right now at considerable cost. So actually, I think that's an additional thing to think about, is that in fact we may need access to some of that coal for maybe 50 years, perhaps even longer than that, just to affect the transition. We always wondered what your thoughts on that were.
Well, one of my favorite sayings is don't let best become the enemy of good. And that's often something that's very challenging to grapple with in the sustainability field. We all have, getting back to those definitions of sustainability, and something is only sustainable if you can continue doing it forever. Obviously, that's just simply never going to be the case. And as a result, we're going to require several generations of different types of energy technologies in order to ultimately move towards something that is more sustainable. And so in the environmental field, unfortunately, there's a lot of, I guess you'd say, infighting, so to speak, about which green technology is better, or because a certain technology is not as good as, say, a perfect solar system, solar energy system, we shouldn't adopt it. In reality, is we're going to require almost everything we can get in order to move forward. Sometimes it means adopting a less bad transitional technology just to sort of open up a market sector and get adoption and get consumer buy-in. And we've certainly seen that with hybrid vehicles. Because you sort of had these inroads with hybrid vehicles that really they're certainly a major improvement in terms of energy efficiency, but on a grand scheme of things, relatively low incremental gains efficiency-wise. But because we had this technology and people began to buy into it, it became a part of our sort of normal lexicon of transportation. It sort of paved the way for other types of technologies to take place. So I think there's a lot of argument to be made for starting now and not waiting for the perfect solution to come about. But with that said, I think we also have to be careful that any transitional technology we adopt along the way, there's a chance it could stick. There's a chance it could turn into a permanent technology. And so we have to be comfortable with the risks and the trade-off that each technology engenders. And so that's why things like thinking about the minerals or thinking about the waste streams will be essential. And I certainly agree with your point that we can't wait until it's a problem to begin dealing with some of this. And finally, I would say, with respect to the climate issue, I know you said that aside, but, carbon dioxide has a 100-year lifespan on average in our atmosphere. So even if we stopped releasing any greenhouse gases right now, the net, it will take the atmosphere a while to equilibrate, and the net CO2 concentration in the atmosphere would end up going up, even if we stopped right now. And so getting back to that core environmental argument, we really have to be proactive about any improvements we can get on the short term that can hopefully help transition us to longer ones to better ones in the long term. But it's always a careful balance between willingness to adopt, potential risks, the environmental risks if we do not adopt, costs, etc. And so that's where we get into methodologies like LCA, and then also methodologies like multi-criteria decision analysis, which is increasingly being used for these kinds of renewable energy deliberations, because we do have to take into account social risk, economic risk, etc. I don't know if that was really a direct answer, but sort of tangential.
I think the other side of the 170 years is, the good news is a lot can happen in 170 years from the point of view of technology.
I hope so.
And if we look back 170 years, I think 170 years ago we were messing around with a steam engine. We were building railroads, and that seemed to be the technology of the day. Things have changed somewhat. So there is some hope that some radical train of thought, perhaps regarding transportation in particular, can improve our efficiencies at least.
Right, and I think that hopefully the intro that I'll do, the intro to the life cycle lecture will echo on this, because the other challenge to this is that even 170 years ago, the things we were doing then still echo in the technology we have now. And so that's one thing we always have to be mindful of, is that technology is cumulative. And so we're never going to be able to make these really dramatic step changes that we think, we're always going to be borrowing some of the past technology to move forward. And so we have to be cautious of what we consider to be technological lock-in. That's the idea that very early decisions, like a decision to adopt automobiles for personal transportation instead of, say, the horse, have locked us in to a certain type of infrastructure. They've locked us into a certain type of urban development, to a certain type of vehicle, fuel use, etc. And so that trajectory was really set a very long time ago. And so even though I think we have to think about transitional technologies, we still have to be aware that there is a risk that it may not be transitional. We may lock into a technology, and then as the farther you go down the technological progress curve, the more difficult it is to then transition to another technology without major economic disruption. And I think that that speaks to the need for collaboration with people who study phenomenon like that. So social scientists, behavioral economists, policy analysts, historical anthropology, those fields, while we don't necessarily think of them as being stakeholders in a renewable energy dialogue, they can tell us a lot about how behavior, historical patterns, etc., inform technology adoption, which will be very important for moving forward.
Any questions from me?
I have one. Do you know, you mentioned the cost of fullerenes to produce 1 kilogram, the amount of energy you needed. Do you know what the cost would be to produce a doped semiconductor, if that's on the same scale, or is it more or less as far as energy?
I'm sorry, I'm having trouble hearing the question.
I guess there's a question about the comparison, let's say, of the cost to produce a kilogram of a fullerene. Do you have access to any information for certain types of doped semiconductors? But it's going to
Like
vary.
inorganic, as compared to organic.
This figures out, right? The cost, if you got doped silicon, you can get that cost per kilogram. You can get cadmium telluride. So
It seems
Right.
like
Yeah, so the best person to ask will be, and I think that we'll be sending a couple papers for you all to read. And in one of the papers that Anik and I published a couple years ago, we actually looked then at, once you integrate things like, and this, we looked at C60, C70, she also looked at multi-junction, single junction cells. Once you integrate the nanomaterials into the cells and then integrate them into sort of into the device, when you look at the energy payback over compared to, one of the challenges, first of all, is it's very hard to compare things like organic photovoltaics, which is what the fullerenes will probably be used in, to the traditional photovoltaics, because they're not necessarily going to be competing in the same market. They're going to be more competing in sort of like roll-to-roll, flexible, color, clothing, things that have a more specialty market. So it's a little bit difficult to compare apples to apples, because when you think about the amount of they're better for low incident insulation. When you start thinking about that, it's a little bit hard to compare them to apples, but even when you integrate these into devices, it typically comes out lower on a life cycle energy input than silicon and traditional technologies. We certainly, in one of the papers, we actually show that comparison, and they're relatively low even with some of those uncertainties. But I believe that Anik will be able to answer that hopefully on Monday. I'm sorry if that was a confusing question, but we'll be sending those papers out to the group to read.
Well, thanks, Callie, we really enjoyed that.